11G, antidifferentiation of circular functions. Today we're going to learn about how to antidifferentiate various circular functions. What you need to be able to do is recognize the rule required for each of the three circular functions that we're familiar with, sine, cos, and tan, and use the chain rule if required to antidifferentiate. Now, it's not exactly the chain rule, but it's that concept of if you have a composite function, how could you antidifferentiate it? So we're going to start straight off the bat with some rules over here. These rules will seem familiar because we know how to differentiate our circular functions already. So I'm going to kind of explain it for this first one here. To integrate sine x, it goes to negative cos x plus c, and that should lay the groundwork for the other ones. Let's consider for a second differentiating cos x. Whoops, not equals, differentiating cos x. If I were to differentiate cos x, that would become negative sine x. So think of it like this. This is the integrate column. This is the differentiate. So when I differentiate this is the answer that I get. So when I differentiate cos x, I know that I get negative sine x. So how do I make that negative a positive? Well, what if I differentiate negative cos x? Then I end up with a negative, which makes it a positive. So that's the idea. I'm just going backwards. That's all it is. Differentiating cos gives me negative sine. Differentiating negative cos gives me positive sine. So when I integrate, think of it as going backwards. When I antidifferentiate sine x, I get negative cos x. So that's kind of the explanation as to where these rules come from. And then it's just a matter of applying that same concept to the rest. Of course, as we have seen with all of the different functions we've been doing so far, if there is any kind of function within a function, so this is our composite, what we need to do is just divide by the gradient. So in here, the gradient is kx plus a, so we're going to divide, that's the function. The gradient is just k, so therefore we're going to divide by k. As always, this should be a linear factor that's on the inside, otherwise this rule doesn't work. So sine, as we said, goes to negative cos. As you would imagine, when I differentiate sine, I get positive cos. So when I integrate positive cos, I get positive sine. When I differentiate tan, I get sec squared. So when I antidifferentiate sec squared, I get tan. With all of them, you can notice that whatever the gradient is on the inside is what I divide by. So that's your main rules, and that's all you need to know going ahead for this exercise. So let's go ahead and start applying these to some questions. Example 19, find an antiderivative for each of the following. So first part, sine 2x minus cos 4x. So the main thing is to just remember what are the rules. Remembering that sine goes to negative cos, and we also have our gradient on the inside. So our gradient in this case is 2. And because it goes to negative cos, I'll have a negative on the outside. So that'll be negative a half cos 2x. And then cos goes to sine. So that'll be negative, and the gradient is 4. So that'll be a quarter sine 4x. Part B, antidifferentiate cos 2x minus pi on 2. I think I forgot to do this with the previous question, but this is the appropriate thing to do. Write it out properly first. I mean, if I go back, I just wrote the answer straight away, but this is your way of showing a little bit of working out, which I think is nice to do. Okay, cos, as we mentioned, cos just goes to sine. And we can also see that the gradient there is 2, so that we will divide by 2 there. Everything else just remains as it is. Now, one other thing that you might notice is that I'm not writing plus c. Why am I not writing plus c? It's because it's asked for find an antiderivative, not find a or not find the antiderivative. If it's the, I must always put a plus c. But remember, when it says an, what we can do is, we can put any version of c. So c might equal to 10. So I could write this plus 10. That's totally valid. I could write plus 1,000. Totally valid. I can also write just 0 or nothing at all. So if you want to include the plus c, that's fine. You're not going to lose any marks. But all of these are where c is equal to 0. I just skipped over it just because we've done that previously. But it just, to highlight that just in case you've forgotten about it. Okay, next question, example 20. Find the exact value of each of the following definite integrals. So it's not asking for the exact area. I don't have to sketch anything, but it's just asking me to find the exact value. So we'll need to integrate it, sub in the boundaries, and find the answer there. So sine goes to negative cos. So I'm going to have negative cos, and I can see that the gradient here is 2. So I'm going to divide by 2, and I will have 2x in the brackets there. I will then put in my boundaries, 0 to pi on 4, and I'm going to substitute these in. So that'll be a negative 1/2 cos 2 times pi on 4 minus, and then negative 1/2 cos 2 times 0. Now, the first one, 2 and 4 can cancel out to be 2, and then I'll have cos of pi on 2, which we know is 0. So this factor here, or this term rather, will just be 0. Here, 2 negatives make a positive, so I'll have 1/2 cos 2 times 0. 2 times 0 is just 0, and we know that cos of 0 is 1. So I will just have plus 1/2. Oops, I meant that in black. And then finally, 0 plus 1/2 is 1/2. Part B, very similar again, sine goes to negative cos. In this case, our gradient is 1/4. So when I divide by 1/4, it becomes 4. So I'll have negative 4 cos x on 4, and then cos just goes to positive sine. The gradient here is 2, so I'm going to divide by 2. Write our boundaries out, sub it in. And remember, we do minus. Now I'm going to subtract each of these terms. Actually, just so, because there's a lot of negatives already, I'm just going to put it in brackets. So that'll be negative 4 cos 0 on 4 minus 1/2 sine 2 times 0. I think one more bracket. All right, let's go. So cos pi on 4 is 1 on root 2. Actually, if I write it as root 2 on 2, that'll be nice to cancel it out. So 1 on root 2, or root 2 on 2, same thing. Next one, 2 times pi is just sine of 2 pi, which is 0. So that's really nice. That cancels out. Then I've got the minus and the bracket. Cos, this will just be 0. Cos of 0 is 1. So that'll be negative 4. And then again, I've got sine of 0, which is just 0. Okay. So what I'll have left over, the 2 and the 4 cancel out to give me a 2. And then the 2 negatives here are going to form a positive. So I'm going to end up with negative 2 root 2 plus 4. All right, part C. Very much the same as before. The gradient here is 3, so we're going to divide by 3. Cos goes to positive sine. Bracket stays as it is. Write out the boundaries. Let's substitute everything in. So that'll be 1/3 sine 3 times pi on 3 plus pi on 6 minus 1/3 sine 3 times 0 plus pi on 6. All right, let's simplify this. So the first thing is that the 3 and 3 cancel out, so I end up with a pi, and then I'll have pi plus pi on 6, which will be 7 pi on 6. So I'll have 1/3 sine 7 pi on 6 minus, and then 3 times 0 is just 0, so I'll have 1/3 sine pi on 6. Now, 7 pi on 6 is in quadrant 3, and we know that sine is negative in quadrant 3. So sine of pi on 6 is 1/2, and because it's in the third quadrant, it's going to be a negative. So I'm going to have 1/3 times negative 1/2 minus, and then sine pi on 6, this is in quadrant 1. Sine is positive in quadrant 1, so that's just going to be positive 1/2, so that'll be 1/3 times positive 1/2. So this will end up being negative 1/6 minus another 1/6, which will be 2 on 6, which will be negative 1/3. All right, next example, example 21. So this time they're actually asking us to calculate the exact area. So when we're calculating the exact area, it is so important to sketch to be able to recognize whether that area is above the x-axis, below, whatever it is, if we need to split it up. So it wants us to calculate the exact area of the region bounded by between this curve, between the x-axis and the line x equals 3 pi. So let's go ahead and draw this just so that we can understand what it looks like, and then we'll go ahead and put in our boundaries. So this is a sine graph where the period is 2 pi divided by 1/2, which means that the period is actually 4 pi. So let's go ahead and draw that. So that's going to be 0. This will be pi, 2 pi, 3 pi, and 4 pi. So now we just need to figure out what region we're talking about. So it's between the curve, so wherever the curve is here, between the x-axis, so where it's bound between the x-axis, and then the line x equals 3 pi. So where do we have a boundary between the curve, the x-axis, and 3 pi? You might be able to see it. If I cut 3 pi there, hopefully you'll be able to see that's the curve, that's the x-axis, and that's 3 pi. So the area that we're talking about is this one here. Now what we can hopefully also see is that this is a negative area. So if this is my area 1, then the way to work this out is that I need to integrate negative area 1. Okay, we have pretty much all the information that we need. So I want to integrate from 2 pi to 3 pi of sine x on 2, and I've put the negative out the front because it is below the x-axis. All right, sine turns into cos, negative cos rather. So I've got a negative on the outside, that's just that one. And then in the bracket, I'm going to have negative cos x on 2. Of course, we shouldn't forget our gradient. So the gradient of the inside is a half, and then we're going to divide by half. So when we do 1 divided by half, I get 2. And that'll be from 2 pi to 3 pi. Okay, before I even go on, I'm just going to cancel out these negatives straight off the bat, so I don't have to worry about them. I just pull out the negative. And then I'm going to go ahead and start substituting in. So that'll be 2 cos 3 pi on 2 minus 2 cos 2 pi on 2. Now, cos 3 pi on 2 is just 0. It's over here on the axis. So this is just 0. And then here, cos 2 on 2, so that's just cos of pi, is going to be negative 1. So I have negative 2 times negative 1. So that is going to end up being 2 units squared. Example 22. I think this is the first time we've seen these kinds of questions where we have to find the value of k by solving the following integrals. So they actually give me the answer of what the value of this integral is, and what I have to do is I have to find that upper boundary. Really, it's just going to be a bit of a substitution and algebra game. Might look a little bit confusing at first, but as soon as we do it, you'll see that it's just, as I said, a little bit of algebra. So what we know is that when we integrate 4x cubed between 0 and k, the answer is going to be 27. So let's go ahead and do that. Let's integrate it. So we add 1 to the power, which means that that's going to be x to the power of 4, and we divide by the new power, and that's between 0 and k, and that whole thing should equal 27. I'm just going to simplify it to make my life a bit easier. And then I'm going to go ahead and sub in k. So I'm going to get k to the power of 4 minus k to the power of 0 equals 27. Of course, k to the power of 0 is just 1. So I get k to the power of 4 equals 27. I'm then going to take the fourth root of both sides. And I have no idea what the fourth root of 27 is. It's not an exact value, but it's just 4 root 27. Now, of course, when I take an even root, so a square root, 4, 6, whatever it is, I can always get plus minus. But as k is at the top, the assumption is that it is greater than 0. So we usually have the boundary on the top is larger. So that's why we just assume that it is going to be the positive version of it. Part B, very similar again. So if you remember integrating e to the power of x on 2, what we have to do is just divide by the gradient of the inside. So in this case, the gradient of the inside is a half. When I divide by a half, I get 2. So I get 2ex on 2, 0 to k, and this time it's going to equal to 4. I'm going to do the exact same thing as before, where I'm going to just sub it in. Sorry, that should be 0 on 2. Okay, so simplifying that, e to the power of 0 here is just 1. So that'll be 2 equals 4. I'm going to take the 2 to the other side by adding it. So that's going to equal 6. And then I'm going to divide both sides by 2 to get rid of it. So that'll be ek2 is equal to 3. Then to take the e over, I'm just going to take the log e of both sides. And then I'm going to multiply over by 2. So that is the value there of k. You can also simplify a little bit further if you like by taking the 2 as the power. If you do that, you get log E 9. All right, last one. A little bit more complicated here. They've actually given me a boundary this time, 0 to pi on 2. You'll see in a moment why we're going to need that. And yeah, other than that, we'll just go ahead and try and work this out. So cos goes to sine, and we've got a gradient of 2. So I'm going to divide by 2. So I get a half sine 2x from k to pi, and that's going to equal negative root 3 on 4. We'll go ahead and substitute in as always. Okay, now sine 2 pi is just 0, so that whole term there is going to be 0. And I end up with a half sine 2k is equal to negative 3/4. If I want to get rid of that negative half, I'm just going to multiply both sides by negative 2. So that's going to cancel that out. I end up with sine of 2k is equal to negative root 3 on 2. Hopefully you can kind of see where we're at right now. We're just at solving a circular function, and where in this case k is my angle, and that's why they've given me this boundary 0 to pi on 2, which means I'm just going to be working in quadrant 1. So we're going to do what we usually do. We're going to start off by finding our base angle. So sine of what gives me root 3 on 2. Don't worry about the negative, but that's going to be sine, it'll be, the angle is usually pi on 3. Because we want our first quadrant, before we get there, the angle is negative. So where does that happen? That happens in quadrant 2 and quadrant 3 and in quadrant 4. So in quadrant 3, I've just realized actually, I did a very silly mistake. Negative times negative is positive. I just thought that was a bit strange because obviously they've indicated quadrant 1 and it doesn't make sense to be quadrant 3 and 4. So hopefully you picked that up. It's an absolute classic Sophie mixing up the negatives. So here you go. Hopefully you picked that one up. All right, back to this one. So where is sine positive? We're in quadrant 1 and in quadrant 2. Now I know that this is just saying quadrant 1. However, because there's a 2, remember that our period is going to be halved. So that's why I do need to consider quadrant 2, because in a sec, all of my angles are going to be divided by 2. All right, so in quadrant 1, that looks like pi on 3, and in quadrant 2, that looks like 2 pi on 3. I remember that's what 2k is going to equal. Obviously, this is outside of my domain for now. However, I need to get k by itself, so I'm going to divide everything by 2. So I get pi on 6 and pi on 3, which are both in the first quadrant. To test this, what you can always do is substitute in these values of k, and you'll notice that this should be the answer. That's something that you can do to check if you'd like. Other than that, that's the end of this exercise. Please go ahead and complete some of the questions to practice. See you later.